Hi everyone, welcome back to the channel. So today I'm here with another lesson of our DSA lesson series, and we are going to explore one of the most important ideas in data structures, AVL rotations. But before we jump into rotations, we need to understand the path that leads us there. So let's begin at the foundation, the binary search tree. The binary search trees follows one key rule, which is every value is smaller than a node goes to its left side. Every value greater than a node goes to its right side. So here you can see I have insert 8, then I insert 5, it compares with 8, it's smaller than 8, so it goes to left side of 8. Then I insert 3, it compares with 8, it's smaller than 8, so it goes to left side of 8. Compares with 5, it's smaller, so it goes to left side of 5. Then I insert 10, compares with 8, it's greater than 8, so it goes to right side of 8. Then I insert 6, compares with 8, it's smaller than 8, so it goes to left side of 8. Then it compares with 5, it's greater than 5, so it goes to right side of 5. So the inserting process, the deleting process, the searching process of binary search tree works upon this major rule. But the biggest issue with binary search trees is that these trees can become imbalanced. For example, if we insert values in a sorted order, just like this, the tree starts leaning heavily on one side, as shown in this figure. Instead of looking like a tree, it will stretch out as a chain, almost like a linked list. So this will result in worst case performance, and will ruin the purpose of using binary search trees. To understand imbalance, first we need to talk about height. Height can be simply defined as the number of edges on the longest path down to a leaf from a node. So if we take 8 here, height of the left side of 8 will be 1, 2 and 3. I chose this path because it's the longest path. I could have chose this path which goes from 8 to 6, but it won't be the longest path because it will give us the height of 2, 1, 2. So it's not the longest path. The longest path is the path goes from 8 to 2, which will give us the height of 1, 2 and 3. So height of left side of node 8 will be 3, height of right side of node 8 will be 1. So I think you got an idea about how the binary search tree works and how to calculate the height of a node. To solve the unbalanced tree problem, computer scientists created self-balancing trees. These trees automatically rearrange themselves whenever an insertion or deletion makes them too tilted to one side. So few of them were AVL trees, red-black trees, splay trees. So one of the earliest and most popular self-balancing trees is the AVL tree. So this AVL tree used balance factor to determine if the tree is balanced or not. Then if the tree is imbalanced, the AVL tree makes some movements, some rotations to make itself balance again. So these rotations are called AVL rotations, and that's the topic what we are gonna learn today. To do rotations to balance out a tree, first we have to check if the tree is balanced or not. To check that, we use balance factor. So the formula for balance factor is height of left sub tree minus height of right sub tree. uh, earlier we got to know how to calculate height. We just take the number of edges on the longest path down to a leaf. So as the height of left side of node 8, we can take 1 2. Alright, as the height of right side of node 8, we can take 1. So this calculating of balance factor happens when we insert a new element or when we delete the element, because it will change the height of nodes, right? Now let's insert this element to our binary search tree. Compares with 8 is smaller, so it comes here. Compares with 5, it's smaller, so it comes here. Compares with 3, it's smaller, so it goes here. Now we calculate the balance factor. You should keep in mind that every leaf node have the balance factor of 0. Okay, and the balance factor can range from -1 to +1. It can be -1, 0 or 1. If it exceeds 1 and become 2, or if it exceeds -1 and become -2, then we can say that the node is imbalanced. So let's calculate the balance factor. As you know, leaf nodes have balance factor as 0. Okay. Node 3, height of left subtree is 1, height of right subtree 0. 1 minus 0 equals 1. This is a leaf node, so balance factor is 0. Here balance factor, height of left subtree is 1 2, height of right subtree 1. So it's a +1, it's within the range, so the node is balanced. Then we have this is a leaf node, so balance factor is 0. Now we have this height of left side of node 8 will be 1 2 3. Height of right side of node will be 1, so it becomes 2. Now we know that the balance factor can range only from -1 to +1, so we got 2 here, right? So that means this node, the node 8, is in balance. So to make this balance, we have to do rotations. When doing rotations, you have to keep in mind that always only three nodes will engage in a rotation, and how we can choose those 3 nodes which are going to be engaged in the rotation is that first we get the unbalanced node, which is 8 here. Then its heavier child is 5, right? We take 5. Then its heavier grandchild is 3. The nodes 8 5 3 will be affected from the rotation. To decide which rotation to use, we look at the shape of the imbalance. There are few topologies that you will hear about. First one is straight leg. This pattern happens when the imbalance occurs in a straight line, as shown in the figure, right right or left left. And the second one is dog leg. So this pattern happens by bending in the middle, like right left left right. And also sometimes you will hear the term spider leg, which refers to more spread out shapes, but the idea is the same, just we are identifying the direction which the tree is leaning. After finding the shape of the imbalance, we can move to rotations. So first we will look at the straight leg rotations. Here we have the right case. In the right case, we do a left rotation. So we have our nodes x, y, z. So let's calculate the balance factor first. Since z is a leaf node, it will be 0. Y, there is no left child, so left height is 0. Right child, we have height of 1 equals -1. It's balanced. And let's go to the node x. No left child, so height is 0 minus right child, we have the height 1 2 equals 2. So x became unbalanced. Because of that, we need to do a rotation. So we do the left rotation, which will bring the median element. The median element is y. Median element as the root, as you can see here. Okay, then we move to the left case. In this case, we do a right rotation. So here we have our elements z, y, x. Let's calculate the balance factor first. Since this is a leaf node, balance factor will be 0. Left child height is 1. Okay. Right side height is 0. So it is 1. It's balanced. Then we go to x. Left side height is 2. 1 2. Right side height 0. So now we know that z is unbalanced, so we have to do a rotation. In this case, we do a right rotation. Also in this case, the median element will become the root. As you can see here, y became the root after doing the rotation, and z came here, x is down here. Now let's look at the dog leg cases. First one is right left case, where we do a right left rotation to balance the tree. So first we will calculate the balance factor. Since this is a leaf node, the balance factor will be 0. Height of the left side 1. Height of the right side 0 equals height of the left side 0, because there are no any left elements, minus height of the right side 1 2. As you can see, x became imbalanced. So to balance this pattern here, we use 2 rotations. First one is a right rotation, the second one is a left rotation. So we combine these together and we do a right left rotation. So let's see how the first right rotation works. First right rotation goes as the last element comes as the median. So here you can see elements are in the order x, z, y. It will become x, y, z. The y in the last node comes as the median. Then we do the left rotation. As you can see here, after the y came as the median, we can see that it's a straight leg pattern, right? The dog leg pattern has become straight leg pattern. So now we have to do a left rotation to get the median element as the root. As you can see here, we will do the left rotation. So the median element y will become the root, x will go down here, and z will stay here. So that's how the right left rotation works. Now let's see the left right case, which we use the left right rotation. So here we have the left right case. First we will calculate the balance factors. This is a leaf node, so balance factor is 0. Left side height 0, right side height 1 equals -1. It's balanced. Left side height 1, 2, right side height 0 because there are no any right side elements. 2. So now you can see the Z is unbalanced. To balance this out, we use left right rotation. First we do a left rotation, then we do a right rotation. So after combining them, we call it left right rotation. First we do the left rotation as shown in the figure. The last element moves to median place, where the y moves to between z and x, as you can see here. Now it has become a straight leg case, right? The previous pattern was szxy, now it's zyx. So now we have a left case in a straight leg pattern. So we do a right rotation here, where we bring out the median element as the root and other elements as the child. So x will go here, y becomes the median, and z goes here. So that's how the main 4 types of rotations work. First one is left rotation. We use that in the right case. Second one is right rotation. We use that in left case. Third one is right left rotation. We use that in a right left case of dog leg pattern. Fourth one is left right rotation. We use that in left right case of dog leg pattern. Now I will move with the practical example, so you will have a better idea about how these rotations work. So what we're going to do is that we are going to insert these values into our AVL tree. So first I insert 40, balance factor is 0, no problem. Then I insert 20. 20 comes here, compares with 40, it's smaller than 40, so it goes as the left child. Okay, then we calculate the balance factors. This is 0, this will be 1 because 1 minus 0. Then we insert 10. 10 comes here, compares with 40, it's smaller than 40, so goes to left side. Compares with 20, it's smaller than 20, so goes to left side. And we calculate the balance factors. This will become 0 because this is a leaf node, and height of left subtree is 1, height of right subtree is 0 because there are no any elements. Height of left subtree is 2, 1, 2. Height of right subtree 0 because there are no any right side elements, and the balance factor will be 2. So we know that balance factor can range from -1 to +1, but this is 2, so this becomes imbalanced. To make this imbalanced tree balanced again, we do a rotation. So here we have a straight leg left case, right? As we look at earlier, in straight leg left cases we use right rotation. So we are going to use a right rotation here. As you can see, we will use a right rotation where the 20 will become the median element, will become the root here, and the other elements will become childs, as you can see here. So then I insert 25 here. 20 comes here, 25 comes here. Compares with 20, it's larger than 20, so it goes to the right side. compares with 40, it's smaller than 40, so it goes to the left side. So let's calculate the balance factors. 0, this will be 0. Okay, this will be 0. This will be 1 minus 0 actually. Minus 0 is 1. This will be 0 because this is a leaf node, and here we have left height as 1, right side height 1, 2, so it will be minus 1. The tree is balanced, no problem. Then we insert 30 comes here, compares with 20, larger than 20, so it goes here. Compares with 40, it's larger than it's smaller than 40, so it goes to the left side. Then compares with 25, it's larger than 25, so it goes to the right side. So let's calculate the balance factors. Balance factor will be 0 because this is a leaf node. Then this node, height of the left subtree is 0 because there are no any elements. Height of the right subtree 1 equals minus 1. Then we have this height of the left subtree 1, 2. Height of the right subtree 0 because there are no any elements. Now the balance factor will become 2, so this node becomes unbalanced, so we choose this node, and this node to do the rotation. As you can see here, this is a left right case of dog-leg pattern. In the left right case of dog-leg pattern, we use left right rotation. Okay, I think you guys can remember. Okay, first we do a left rotation where the last element will become the median element. Here you can see we have the pattern 40, 25, 30, so it will first become 40, 30 and 25, as you can see here, 40, 30 and 25. So now it has become a straight leg left case. So in left cases we use a right rotation. So here you can see we use the right rotation where the median element will be the root and other elements will become its child. So as you can see here, we have 30 here, 40 here and 25 here. So this tree is balanced again. Now let's enter 22. We had 22, compares with 20, it's larger than 20, so it goes here. Compares with 30, it's smaller than 30, so it goes to the left side. Compares with 25, it's smaller than 25, so it goes to left side of 25. Then we calculate the balance factors. This will become 0. This will become height of left subtree is 1, height of right subtree is 0 actually, because there are no any elements, so this will become balance factor is 1. Here we have 40, it's a leaf node, so balance factor is 0. Here we have height of left subtree is 1, 2, height of right subtree 1, so 2 minus 1, 1, it's good. Here it's a leaf node, so 0. Here we have the height of right subtree as 1, height of left subtree as 1, 2, 3. So after doing the calculations, we get minus 2 as the balance factor of 20. So this node will become unbalanced. Because of that, we will have to do a rotation. We have to choose the unbalanced node, its heavy child and its heavy grandchild, which will be 20, 30 and 25. So as you can see here, this is a dog leg pattern, right left case. So in right left cases we use one right rotation and one left rotation. First we do the right rotation to get the last element as the median element. As you can see here, last element has to come between 20 and 30. 20 and 30, and we have the last element here as the median. Now it's a straight leg pattern which uses the right case, and it uses a left rotation. So now we will do the left rotation, where the median element will become the root, and other two elements will become its child. So as you can see here, this became the 25 became the root, 20 became its child, left child, and 30 became its right child, and the tree is balanced again. Now let's insert 50. Okay, 50 comes here, compares with 25, it's greater than 25, so comes here. Then compares with 30, larger than 30, so it goes here, right side. Then compares with 40, it's greater than 40, so it goes to the right side of 40. And we calculate the balance factors. This will be 0 since this is a leaf node. This height of left subtree 0, height of right subtree 1, so 0 minus 1, negative 1. It's balanced. Then we have 30, height of right subtree 2, 1, 2, height of left subtree is 0 goes, so there are no any left subtree elements, so this will be minus 2, and we know that 30 will become unbalanced. Because of that, we have to do a rotation. We choose the unbalanced node, its child, and its heavy grandchild. Unbalanced node, its heavy child, and its heavy grandchild. So the rotation will happen between these three elements, 30, 40, and 50. Here you can see a straight leg right case. In right cases, we use a left rotation where the median element will become the root again, and 30 and 50 will become its childs. Okay, here you can see 40 became the root element, and 30 and 50 became its children. So that's the practical example. Now we have a fully balanced AVL tree here. So that's how the process of AVL tree rotations works. I think you got an idea about how these 4 kinds of rotations works in the practical scenario, and now let's see the code implementation. Here we have the class node. So this is the core building block of the AVL tree. Each node contains a key, pointers to its left and right children, and a height field. The height field is crucial for calculating balance factors, which determine whether rotations are needed or not. When a node is created, it is initialized as a leaf, so its height is set to 1, and both children are null. There's one quick clarification before we continue. In the theory part, I mentioned that leaf nodes have a height of 0. That's because there we count height based on edges. But in the Java implementation, you might notice that leaf nodes have a height of 1. That's simply because in programming, it's often easier and clearer to count height based on the nodes instead of edges. So just remember, theory uses edges, code uses nodes. Both are valid, just different conventions. Here is the height function. So this function returns the height of a node. If the node is null, it returns 0. Otherwise, it returns the node's height. This is important because the AVL tree uses height of the left and right subtrees to calculate the balance factor, which controls whether rotations are necessary or not. Despite the lack of loops, recursion ensures that when height is called, all child nodes already have their heights updated. So here we have the max function. This returns the maximum of 2 integers. It is used whenever we update node's height as a utility function. And here we have the get balance function, which gives us the balance factor. Okay, now let's look at the code implementation of rotations. First, we will look at the right rotation. Here we have the right rotate function and the y parameter to catch the node, which will be passed as an argument to the function. Uh, the node which will be sent as an argument to this function is the unbalanced node. So here we have a figure which has the nodes 5, 3 and 1. So here 1 is balanced, 3 is balanced and 5 won't be balanced because height of the left subtree is 1, 2 and height of the right subtree will be 0. So this will have the balance factor of 2 and this node will become unbalanced. So this will be the node sent to the function as an argument. Let's look at what will happen inside the function body. So the unbalanced node will get catched by this parameter y, so this becomes y. Okay, then left child of y has been assigned to node x. So left child of y is 3, so this will be assigned to x, so this will be x. Then a right child of x will be assigned to t2. This is x, so right child of x, which means this is not a actual node, this is just the position of right child of x. Okay, we have to preserve this position so we won't lose it during the rotation. So after that we have assign y to the right child of x, so x is this and we have to assign y as the right child, so it will give us something like this 3 over here. Then we have assigned t2 as the left child of y, so this is y, this is the left child of y. As I mentioned earlier, this is just the position we are preserving, not the actual node. Okay, so now we have completed the right rotation, and after that the heights will get updated by these codes. Then we have the left rotate function for doing left rotations. So I'm not going to explain this because this just mirrors the behavior of right rotation. Then we have the insert function. Here with this code we perform the normal binary search tree insertions. Then with this code we update the height of the ancestors of the node. With this code we get the balance factor, and after that we know that there are 4 types of imbalanced shapes. To do rotations, first we have to figure out what type of rotation are we dealing with. So to figure that out, there are 4 if statements here. Alright, so this one, this condition checks if the case is a left case. This condition checks if the case is left right case. This condition checks if the case is right case. This condition checks if the case is right left case. According to the case that we are facing, we will use the relevant rotations to balance out the tree. So for left cases we use right rotation. For left right cases, first we use left rotation, then we use right rotation. For right case we use left rotation. For right left case, first we use right rotation, then left rotation. So that's how the rotations happen inside this Java code. And I hope you guys got an idea about how this rotations work in actual implementation. And that's how AVL trees stay balanced. So in this lesson we covered how binary search tree works, why imbalance is a problem in binary search tree, what height and balance factor mean, the topologies of imbalance, and the 4 AVL rotations, and also how the rotation code works in Java. So these rotations ensure that AVL trees always maintain a small height, giving us fast and reliable operations for searching, inserting and deleting. So I hope this video helped you understand AVL rotations clearly. So if you like the video and find it valuable, drop a like, share it with your friends, and subscribe to the channel, and also click the bell icon to be notified for more videos. Thanks for watching.